MST is one of our sponsors for full disclosure, but we are very interested to hear what they have to say about their product. We think it would be very useful in the Caribbean. They do fiber reinforcement. And David Wolf is, David is going to come and tell us all about it.
Perfect.
So you engineers, listen up.
Great. Well, should I use this, just this mic? Oh, perfect. Can you guys hear me okay? Perfect. Hello, everybody. It's great to be in Trinidad. I'm from Canada, so I'm certainly enjoying the warm weather. Anyway, so my name is David Wolf. I'm the Vice President of Sales and Marketing with MST Rebar. We're based in Toronto, Canada, and we basically sell all over the world. We do a lot of business in the Caribbean already, and looking forward to talking to you about, this is the product here, MST Rebar, which is a GFRP reinforcement. Okay, so I see my presentation is working already, great. So basically, MST rebar or GFRP rebar it's great watching the previous presentations because we're looking at sustainability and green building products. This is actually, it was very interesting hearing the others. I learned a lot about bamboo. It's great to hear as well. This is actually a much more mainstream product as well for use in reinforcement of concrete. And this MST rebar is made to replace all steel rebar. This isn't an alternative. It's basically meant to replace steel rebar in and itself. Oh, sorry, if you could go to the next page. It's just going to go here. I just want to be able to see you. You're not going to take this.
Yeah, and you have a remote here.
Oh, perfect. Thank you. So is this on? Sorry. Can you hear me on it? Okay, good. Okay, so this is just a brief outline of the presentation. I'm going to try to keep this half an hour because I realize, is it working okay? I know that I thought I was going to go after the coffee break, so, well, there we go, perfect. So I want to make sure that I'm just the last presentation before a coffee break can be, everybody can get a little bit tired. So this is just a brief outline. Let me go back here. So this is just an outline here. We're going to talk about examples of corrosion, why use MST bar, changes, the benefits of MST bar, who we are, project highlights, approvals, some other product, thermal break and ultra anchor, and talking about the green nature of this product as well. There we go. So the first thing is, fiberglass rebar, I'm not sure how many of you guys, who's actually, has anybody heard of fiberglass rebar, GFRP rebar, or used it at all? Perfect, okay, great. And out of curiosity, what's your experience been so far? I'm gonna ask you guys questions.
It was a very small project by the a coastal project. It worked well. We chose that because we didn't want any corrosion by the sea, where you usually have when you use steel. It have performed well so far. We don't have any issues. Yeah.
Okay, great.
Have good experience. Yeah.
That answer is exactly what I was looking for. Thank you. I appreciate that. So basically, fiberglass rebar has been around almost for 40 years. And what it used to be used for was corrosion, and strictly for corrosion-resistant projects. But it used to be a lot more expensive than black steel rebar, and there was also very few codes for it. So what's happened? What this presentation is talking about is that this is now becoming, and it depends on where in the world we're talking about. But obviously I'm Canadian, North American. Right now in North America, this is growing exponentially. Our company is basically growing every year. We grow by 3 times. It's basically becoming on stream. Probably the United States is probably the largest growth engine for us. And I'm going to talk about mainly because of the codification, but This is something that now is becoming, I'm going to talk about corrosion, but corrosion really is more of a side benefit now, like what you talked about. And the main benefit is this is a really cost-effective, mainstream reinforcement for all concrete. There's certain applications where it's incredibly cost-effective, and there's a lot of benefits, and there's other applications where there's a little bit of benefit, but in all cases, there's benefits to using this, and it's less expensive than using steel rebar. So the first thing is, this is a corrosion study, Association of Materials and Protection and Performance. Every year in the United, I'll just go, Canada's probably for you guys just a small country way up in the middle of nowhere. But United States, every year, corrosion costs the American economy $500 billion. So it's not a small, it's not a small thing. And if you look at it, I just literally got here late last night, so I haven't spent a lot of time traveling around Trinidad. But in every country I've ever been to, you see constant examples of concrete degradation. Basically, when concrete starts to corrode, it expands. When steel rebar starts to corrode, it expands and breaks and spalls the concrete. There's an example here on the bottom. We're in Florida, where in 2018, I believe, 2018, a tragic accident happened where an entire condo building collapsed because seawater got into the foundation. There wasn't proper maintenance done as well, but the entire building collapsed. And that's strictly from corrosion of steel rebar. So here's endless examples. You see here, these are products, these are structures that are designed for 100 years, last less than 50 years, and more importantly, start to corrode after 8 years. And the thing that happens is that you have these design lives of 50, 100 years, but all that's built into, there's a ton of maintenance and a lot of maintenance costs that are built into this. And when you use MST bar, the products, the structures will last for hundreds of years and with zero maintenance. That's basically the maintenance budget is the only time, for example, on bridges, you have maintenance where sometimes you have to replace the lines on the road, but there is no concrete degradation. So these are, I can go on for a long time, but these are just endless examples here. This is an important one. So this is basically an evolution of rebar, basically reinforcement. So basically, black steel rebar was invented in the 1920s. And post, after the Second World War, there was obviously a ton of construction everywhere. And 50 years later, in the 70s, people realized, oh my goodness, all this concrete structures that we made with steel rebar are starting to fall apart. They're starting to corrode, and this is costing us billions and trillions of dollars. So the first thing that happened in the 70s was the advent of galvanized rebar, epoxy-coated rebar, and then some stainless steel rebar. And the next evolution in the 1980s, the mid-80s, was fiberglass rebar. So this is something that's been around since it's almost 40 years now. It's been here. And basically, what you have here is there's always some arguments whether it's the concrete issue or the steel rebar issue. But when you look back thousands of years ago, and I saw the gentleman previously had some concrete structures in England, rebar has only been used since the 1920s. So all the old structures that are mainly built in Europe, thousands of years ago in Rome, there's a lot of them are still standing because they were just basically built with concrete and not with steel rebar. But back then, if you see here, it was extremely inefficient to design concrete structures without rebar, but they were still built, and a lot of them are still standing. And you see here on the right, this structure that was built in year 2000 in North America with steel rebar is already falling apart. So basically, all steel rebar corrodes. It's just certain the stainless steel rebar corrodes less than black steel rebar. There's all sorts of other things you can do to slow the corrosion. You can use very expensive corrosion inhibitors. You can use vapor barriers. You can galvanize the bar. But all that does is just slow it down and slow down the corrosion and add a lot of cost. So one of the reasons is if this has been around for 40 years and we're starting to see basically exponential growth in the last 5 or 10 years, why is that? What happened? So these are the reasons since basically why there's been this incredible growth in the last 10 years. The first is basically the first two combined there. Overall, anywhere in the world that we've been involved in, the construction industry is relatively slow to adapt to new materials. It's a very conservative industry. People don't want to take risks because you're building large structures. So people are, say, I don't want to work with I'm hesitant to work with a new material. There's a high risk of doing that. But this isn't new anymore. This top section here, the first bridge in the United States was built in 1986 in Virginia. Which is I'm not sure if you've been to that part of the States, but it's a very high snow area, a lot of road salt, and that was built as a test case. This was done, so this isn't new anymore. This is basically, that bridge now is almost, 38 years old, and it's been checked every year. And in 2020, they took out core samples of that bridge, and that was after 36 years, there was zero degradation. The only thing they've done on that bridge literally is replace the yellow line after that long. And that's basically, for any bridge in a snow area with road salt, it's really unheard of. So this basically, there's not really the argument that it's a new product anymore, because it really isn't. And the most important thing is the engineering and codification really has been, and this is in North America, and I know that a lot of the questions here are going to be about the codes, the acceptance, and I want to address all that as well. But and I'm going to talk a lot about that. And there's certain Caribbean countries as well that have incorporated this into their codes as well. So we do, like, just, the list, Bahamas has approved this, Puerto Rico has, Dominican Republic, and Turks and Caicos. Those 4 countries, no specific reason why those particular ones are, but each of the companies that we worked with have basically got into the codes. But basically in North America, the codification, and I'll go into some of the codes. The American Concrete Institute is now on their 3rd and 4th iteration of the codes. So now it's becoming, that's one of the reasons why it's really growing quite quickly. The other is increase in production. Back in 1986, if you wanted to buy a truckload, a container of fiberglass rebar, it took a long time to get, and it was very expensive. Now, because of companies like MST Bar, if you want to import 150 containers next week into Trinidad, it's no problem. We basically, right now, our plant in Toronto produces about 500 kilometers a day of rebar. And now service life, people are finding that you're not only getting 100 years, but now it's hundreds of years of service life. And also support many this is obviously an American presentation here, but many Department of Transports, ministries, and governments are now accepting this, and not only accepting it, actually promoting it, because the governments are the ones that save the money by not having to constantly maintain and constantly replace all of the structures that have been built with steel rebar. And the last one, the most important one, is now it's actually lower cost than using steel rebar. Not over the lifetime, but the initial cost is significantly lower using MST bar than using steel rebar. And that's something that a lot of people don't realize, but that's actually the case, and that's why it's really growing quite quickly. So these are all the benefits. The first one, obviously, is the corrosion resistance. You get hundreds of years of service life, but without any, no maintenance, and you don't require any corrosion inhibitors or vapor barriers, because all the corrosion inhibitors and the vapor barriers are strictly there to protect steel rebar. The other thing is the weight. So this weighs a quarter that of steel. So what that means is that for installation or for placing, the placing time and cost is about half that of steel rebar. Because you can, I'll show you some videos later on, and I want to make sure I'm probably not going to be. I want to make sure I'm not cutting into the coffee break at all. But this is something that makes a huge effect on cost. Also, the bond strength to concrete is 3 times that of steel, so there's no anchoring required with this. You don't need any bent bars for anchoring when you're using this. It's very easy to cut. There's no special tools required. And this is an interesting one. It's actually the fire rating, and this is through ASTM E119, is actually 50% better than steel. A lot of people will think it's a composite, it's a plastic, so there's going to be fire issues here, but it actually is. And I'm more than happy to share. We have literally a mountain of third-party test data of all of these things that I'm talking about here. That if any of you have any questions, please let me know, and I can send it to you as well. The strength, this is 3 times stronger than steel, tensile strength. Fatigue strength is 20 times that of steel, so this works very well in high seismic applications as well. This is an interesting one here, economical curing. I'm not sure what the situation in Trinidad is with fresh water, but in certain parts of the world, we do some business in the Middle East and Saudi Arabia, and there fresh water is at a premium, and fresh water right now I believe, uses about 8 to 9% of all industrial global water requirements in the world for industry. There is no reason to use fresh water in the concrete, because the only reason you don't use seawater in concrete is because it'll corrode the steel. So there is a slight modification of the concrete mixture, and there's a lot of companies mainly in the U.S. and Japan of all places that have one of the larger companies is called Seacrete, that's used for basically concrete that's cured with seawater. Conductivity, there's no grounding required. It's thermally non-conductive. So for example, obviously it's either in very hot or very cold weather. If you pick up a bar with your bare hands, here if it's 40 degrees, it's not painful to pick it up because it's thermally non-conductive. It's also very green as well. So this, from the sustainability point of view, this is 80% less energy to produce 1 bar of steel, but also because it's a quarter of the weight, the transportation costs are also a quarter of that of steel as well. And also the cost is it's lower cost. So this is just an example. There's going to be a lot of afterwards. I've done engineering lunch and learn presentations probably 200 or 300 times, and the ductility question always comes up. I'm not sure if I can. This is a video. I'm not sure. I'm not sure if the video will work on here or not. Oh, here we go. So this is just showing what kind of when you talk about ductility, what kind of basically movement you get in the structure. A little bit about MST bar. We have actually it's a 230,000 square foot plant in Toronto. As I mentioned, we've been tripling every year. Our next expansion will be in the U.S. After that, we're expanding in a plant in Australia, and then after that, we have a plant in the Middle East going in as well. So this is something that is very active because we're starting out from a very small amount. Even though I mentioned we produce 500 kilometers a day, that still we're still less than in the U.S. probably 1% of the total rebar use, but every year it's growing. So everything's developed, designed, and manufactured in North America right now. We're exporting around the world right now. We're the largest pultruder, largest manufacturer of fiberglass rebar in the world right now. We've produced about 1 billion feet of rebar, and we have right now about 20,000 fairly large projects completed in North America. And the current capacity you talked about is, you can always talk about kilometers per year or per day. And then our 2024 capacity which we're in right now, is up to 127,000 kilometers. And we produce only high modulus bar. So that's one of the differences. The main technical difference between steel and fiberglass from a property point of view, the tensile strength is about 3 times that. We're getting around, steel is around 400, 450 MPa, and we're getting approximately 1,300 to 1,400 MPa with MST bar. One of the things from a design point of view, I'm not sure which software all of you guys use here. We've been working with Altair, which is the largest concrete design company in the world. Their product is called S-Concrete and S-Line, and they actually have a specific module just for MST bar. So these are, we have a lot of different examples of projects that we've done. On the left-hand side is quite an interest here with piling. So we basically, we have a caisson design that's used very effectively and very technically effective and also very commercially effective for piles. On the right-hand side is a pier in Ohio, the Port Clinton Bridge, or Port Clinton Pier. These are the caissons that we make. We can either, we manufacture those at our plant, but also, because we'd be shipping here in shipping containers, we can make spiral shapes for the outer caisson, and they can be also fabricated here as well. This is an interesting project in Ontario, Canada. This is the first bridge in North America that has no steel rebar in it at all. Typically, how everything in all countries that we've worked in, everybody, rightly so, wants to start out slow. So for where we typically start out in all countries is we start out with flat work bars, slab on grade work, then progress as people feel more comfortable, the engineering community feels more comfortable, the contractors and the owners feel more comfortable, then we progress further into that. So with bridges, typically the guardrails were the first ones that were started. Then people get into decks. This is the first bridge that has no steel rebar in it at all. All the girders, the columns, everything is 100% MST bar. And this was made cost effectively to steel. It was made, it's expected to last well over 100 years. Well, it came in under budget. It was locally made, obviously, as for Ontario presentation. But it was actually delivered much faster than steel. So from a design point of view, because our capacity is so high, we were actually, the steel rebar would have been actually delayed, and this was done ahead of schedule, and a lighter bridge with less injury as well. Because there was, I have a video here, I think, this is just showing other examples of it. No, the video will come later on. Could you put, oh, I have to do it here? Hold on. Oh, here we go. This is just actually a residential construction video showing basically how you can carry this around. This is something called an insulated concrete form. I'm not sure if this is used in Trinidad. But this skinny little kid here is carrying around a bundle of 25 bars. Is ICF or insulated concrete forms used in Trinidad? Yeah, okay. So this is something that we're probably covering in North America right now about 25% of the rebar used in ICF homes. So because it's such a cost-effective, and technically when you're putting in the vertical bars, when you're trying to do that with steel, there's no comparison between using MST and steel. This is just another example, a large, quite a corrosive application in the farming community in Western Canada. This is kind of a gross application, but it's for animal waste. This is about 100 meters of diameter animal waste tank. That's about 10 meters high as well. These are other examples of bridges. We do precast and cast-in-place bridges as well. This is a bridge, and it's almost like a tourism ad for Northern Ontario. This is Nipigon, Ontario. And this is this is showing the cast in place and precast as well. This is I think one of these is a video coming up. This is the bridge, the 100% MST bridge that I was just talking about before. This is the video. So when you talk about it placing time of being half that of steel, this shows how and why that is. How am I doing on time? I don't know about how many time wise. Oh, I do, but I can. You tell me. You can pull the cane. You can pull me off anytime. I can sit here and talk about this all afternoon if you want.
I'd like to have some questions.
Yeah. So seriously, what time is it?
4:30.
Okay, so we're pretty much okay. So what I'm going to do is I'm just going to show I want to go through just other examples here, but I hate going over time.
Can I ask you a question?
Sure.
And some of your pictures might help.
Yeah.
The first question is going to be from, I'm sure, the contractors in the room and the engineers. Working on site, obviously, we can see that it's lighter to carry around. But traditional reinforcement, we'd have steel benders on site, just bring the steel to bend it to
Yeah.
shape, to cage. This can't quite do that in the same
Correct.
way.
Yeah. So
right?
that's basically that's a great question. So once this is made in a straight bar, it's made with a thermoset resin. So you can't, at the present time, I should say, you can't bend this. We're working on a bendable bar, but it's not commercialized yet. So for all the bent bars, there's a long-winded answer to that question. For the bent bars, we manufacture. I don't have a sample here. I'll get you guys. I have a sample in my. I'll show you samples of bent bar, but it's basically it's a separate process used to make. We can make bent bars in any shape, but one of the things is that a lot of bent bars are used for basically for
Cages.
well, for cages, but also to basically with steel rebar, you need 90-degree bends basically to so it's solid into the concrete, and you don't with steel rebar, the bond strength of concrete actually isn't that high because of the ribs. You have when the concrete goes into concrete is surrounded a steel rebar, and the steel rebar is under tension, it'll tend to neck down and change shape slightly and pull out. So you basically with MST bar, you don't have to. The bond strength is much higher, so you don't need those the bent bars to hold the concrete in place. But with the other thing you can do with we manufacture bent bars to any shape, but also you can actually combine steel bent shapes and fiberglass as well.
Okay.
There's one
See,
question
we
over here.
have some question. I'll ask another one while we get in the microphone over there. Cost, you mentioned cost a few times. Cost to transport is cheaper. Cost to manufacture is cheaper.
Yes.
The overall cost, bar for bar, comparing to steel.
Right now in North America, it's less. One bar of MST bar, what do you guys use? Number 4 or
The
10
4,
millimeter is less money than a bar of steel bar.
With
And
your
with-
fabrication, I noticed that you were saying that you do the fabrication, but I saw some of them you were testing beams. So what do you do in terms of the stirrup? Will we have to send you the dimensions for the stirrups,
Yes.
and then you will bend the stirrups?
Yeah, so the
And-
stirrups, the
and
stirrups
talk
is a
about
good example.
the cost as well associated
Yeah.
with that as well, if you can,
So,
please.
same thing. The stirrup cost will be like a little bit less than the the fabricated cost of the steel. And all I can say is, because I don't have experience in Trinidad, but in the 4 countries I mentioned, the cost it's cost competitive with steel, and most of the time it's a little bit below the cost of steel, including bent shapes.
Okay, talk about the timeline. So say, within what time frame it would take, say if I told you I need 2,000 stirrups, Or say 3,000 stirrups. How long would it take you to bend something like that? Or
3,000
fabricate?
stirrups in our plant would probably take 1 to 2 weeks. And then just the cost, the shipping cost to get it here.
Okay.
Now, one thing I want to introduce, our local our agents, Rendra and Nisha from Freeport. Basically, they're looking at eventually having local inventory here as well, and that'll help with including bench shapes, standard bench shapes as well.
Yeah, very good. Anything? Yeah. Hold on.
Thanks for the presentation. I think this is a very good technology. You also show that it's green, which is good. You mentioned that it also works for seismic design and mentioned fatigue.
Yes.
I should play safe there because fatigue is not only the only specific requirement. There is ductility.
100%.
You show the beams. That beams is not ductile. It's going under cycle.
Okay.
I mean, I'm not saying that technology is not working. It's working perfectly on decks where you have strength, no problem. This is actually a very good name, strength, not necessarily ductility. Typically, probably I'm wrong. I want to ask.
No, you're correct. So I want to address the issue of seismic because seismic relates to the basically the codification. At the present time, the ACI code, even though the properties are very good for seismic, but at the present time in the ACI 440 code, this is actually the seismic hasn't caught up to this design yet, so it's actually not used in the U.S. for high seismic areas.
It's not been used even in Europe. That's what I'm asking.
Yeah, exactly.
This is very good for all, let's say, elastic component. You
Yeah.
show bridges, perfect. Decks, because they are exposed to harsh environment, the icing problem. When it goes to bars, probably you can over-design it, because you can have longitudinal bars being over-designed due to the high strength. But for stirrups, which needs to confine the concrete, hence sometimes they need to yield for active/passive confinement. I'm not pretty sure.
The confinement actually works quite well. The one thing you made a point that I want to address on, you said even in Europe. So the one thing I used to live in Germany. One thing, all the European codes are normally well ahead of most of the world. For this type of product, for fiberglass rebar, the European codes are actually about 10, 15 years behind.
I know. They ask for E-tags, which is a very long procedure.
Yeah.
Yes.
So basically, so right now, the leader in the world for, I want to be really specific, just on fiberglass rebar codes, is that we always have this Canadian-U.S. competition, but the States is really the most advanced, but they're getting, the ACI group, and our CEO, Borna Hajimaraga, is on the ACI committee. They're now evaluating the seismic, and that should be out very soon. It's just not out right now, today.
Thank you.
Luigi, can you give Frank the...
Hi.
Frank has one.
How does your product compare
Well,
with
this one.
basalt rebar?
Basalt, that's a great question. Basalt rebar, the one thing, basalt being a natural fiber, the variability of the strength of basalt fibers is quite high because it's a natural fiber. Basalt will have slightly higher tensile strength than MST bar, but it's also, but when you get into when you're looking at 13 or 1400 MPa, getting a little bit higher really doesn't provide much of a benefit. As an example, we could use carbon fiber instead of glass fiber and have much higher tensile strength, but there's really no practical benefit by doing that. And the other thing is basalt, the capacity of basalt, like there's a couple people that make basalt rebar in the States, but the capacity is minuscule because basalt being a natural fiber, they really don't, they're not able to produce anywhere close to enough of the product. And it's not also consistent enough to be used. So most of the codes, the American codes don't accept basalt rebar.
One more question, anyone? Last one, okay. Thank you very much, David. David
you.
will be here for a little while.
Yeah, I'll be here. Any questions?
Yeah. So
I'll let
any-
either myself, Rendra, or Nisha
Any-
ask it. Any questions? We're more than happy to answer them.
You have a question?
Yeah, because it's glass fiber, right, does the concrete members have more deflection due to it having the glass instead of steel?
Sorry, could you repeat the question? I just didn't hear you fully.
Like, I was doing some reading on glass fiber, right?
Mm-hmm.
And usually what I saw from my research so far, was that it tends to deflect more.
Yes.
Yeah.
So you'll get, so what, basically there's a long, also every question is a long-winded answer, but sorry, but they basically, when you're designing with this, a lot of questions, a lot of times people ask about yield, the steel yielding and yield. So basically when a concrete slab starts to yield, you get all sorts of cracks underneath. The mode of failure with MST bar is different. You can get much high, because you'll never, on the bottom layer of the rebar, you'll never reach the yield point of MST bar. The mode of failure is actually compressive failure of the concrete on top, because you get massive deflection. But the thing is though, once you get, you'll probably get 3 or 4 times the deflection you would with steel. But the difference is that once your load is gone, the product goes right back up to its original shape, and you don't have to dispose of it. All you have to do is do minor resurfacing of the concrete on top, but the overall structure, when a slab made with steel rebar yields, it doesn't collapse, but you throw it away. You have to completely replace it, and that's not the case with MST bar.
Thank you. As I said, David Wolf will be here if you have any further questions. We're going to have a coffee break. We'd like to thank MST, not only one of our sponsors, but we like to bring things to you that engineers need and are relevant. Next year, we'll have Angostura sponsor.
Yeah.
Nisha in the corner there is the local rep. You can speak to her or her assistant, Rendra. Thank you. We'll have a little coffee, and then we come back for...
Thank you. Appreciate it.